Okay, in this clip we're going to talk about substitution reactions of alkanes, and the page references for the OCR textbook are 124 and 125. If you haven't had a look at the clip where curly arrows are explained, I suggest you do that now, otherwise you will be lost pretty early in the clip. Right, okay. So, by the end of this clip you should be able to describe and represent the substitution of alkanes. Now, what we're going to do is we're going to substitute hydrogens in alkanes with a halogen. So we're going to make haloalkanes, okay, and this is also known as the halogenation of alkanes. And the way this works, I suppose, is by a process called radical substitution. Now you'll remember that substitution is defined as replacing an atom or a group of atoms with something else, right? Pretty simple, it's as the name suggests, right? Substitution. But as with anything in chemistry, we need certain conditions for this to work. And the conditions are UV light. We need to have UV light when it comes to actually making this process happen. For this process to begin, we need UV light, or indeed a temperature of 300 degrees C. And there's nothing else to it really, that's the main concept. So, what is involved in the halogenation of alkanes? Well, there's three main stages, and you need to be able to represent each stage, and you need to be able to represent it using curly arrows, okay? These sorts of questions, radical substitution, and indeed any mechanism whatsoever where you're asked to, well, describe or explain any sort of process or reaction, serious mark gatherers, okay? They give you loads of marks, so make sure that you can do this fully. Right, okay, so let's start off with the three stages are initiation, propagation, and termination. We're going to go through each one individually. So let's start off with initiation. Now, the definition for initiation is it's the first step of radical substitution, and it produces free radicals by UV radiation. Now, you'll remember that free radicals are simply species with unpaired electrons, right? So, in this first step, we're simply making radical species, and we need the presence of UV light. Okay, so what actually happens? So, well, let's start off with because there is halogenation, we need halogens. So let's start off with chlorine, because chlorine is the most popular one. Okay, so let's start off with a chlorine molecule, Cl2. Right now, what happens to this chlorine molecule? It breaks down by homolytic fission. It breaks down by homolytic fission to give two radicals of chlorine, okay? Two chlorine radicals. It's as simple as that. So we've got this covalent bond, and it's broken down by homolytic, it's broken down by homolytic fission. Okay, so that's the first step. It's the simplest out of them all. As you can see, we've just made two chlorine radicals from one Cl2 molecule. Easy enough. Now the second step. The second step is defined as the two repeated steps in a radical substitution that build up the products in a chain reaction. Essentially, in this situation, what is actually happening is we are making the haloalkane. We are making the haloalkane. And as you can see, it's two repeated steps, okay? So two steps that build up the products, okay? Now these products are, of course, haloalkanes. Right, okay, so what is the first step? Well, what is the first step of propagation? Well, you'll recall that from initiation we made a chlorine radical. So, perhaps we should start off with that. So let's start off with a chlorine radical. And remember, this is all to do with the entire process is known as the halogenation of alkanes, okay, or the radical substitution of alkanes. So let's react the chlorine radical with the simplest alkane, methane. So what we're going to do, I'm going to actually draw out methane, because we're actually going to show what happens using arrows. Sorted. Okay, so I'm just going to change to a different color to show what actually happens to the bonds. Right, now chlorine has a unpaired electron, as seen by this dot. What happens is, one of the CH bonds in the alkane, any CH bond, it matters not, right, it breaks down, and because it's a covalent bond, there's two ways it can break down, heterolytic or homolytic fission. We're going to break it down using homolytic fission to produce two radicals. So this CH bond, it breaks down by homolytic fission. So we've got a H, so that's going to produce, essentially, I'm just going to draw it underneath just so you can see. Essentially it's going to make a H radical, whoops, and it's going to make a CH3 radical. I'm not sure with that. There we go. So what happens is, this H dot radical can react with chlorine, right? It can react with chlorine, with this chlorine radical, right, to form hydrogen chloride. Let's show this in orange. Okay, now I'm going to use this hydrogen here. So, because it's the same thing, we've just shown it as that. Essentially, this is that there. So, what we're going to have is, they're going to come together, they're going to each donate its one unpaired electron, and it's going to make HCl. And of course, we've got the CH3 radical left over, so we're also going to make CH3. So those are the two products in the first step for propagation. Simple enough, right? Okay, so what is the second step in the propagation reaction? Well, the second step, what we're going to do is we're going to use the methyl radical that we've made in the first propagation step, and we're going to use it in the second step, right? Pretty logical so far. So I'm just going to draw it out. Now, one important thing while I'm drawing this out is you have to recognize that it's the carbon atom which has the unpaired electron. It's not the hydrogen atoms, it's the carbon atom in the CH3 which actually has the unpaired electron. Okay, so we've got the CH3, and what we now do is we just react it with chlorine, because that's what we started off with. So we react it with a chlorine molecule, so Cl2. I wonder what happens. Well, it's pretty much the same step as earlier, right? Except, you know what, we're just going to change one slight bit. It's just going to make it a little bit easier to see what happens. I'm just going to check. Whoops. Don't know what happened there. Right. Just going to... Oh, God. So annoying. Sorry about that, folks. Okay, so we're just going to change the actual position of the... where the radical is and which bond we actually broke. Now, what actually happens is we have the same thing happening. We break up this Cl2 molecule by homolytic fission to produce radicals. One of the chlorine radicals, so we're going to choose the one on the left, will react with the CH3 radical, right? So we're going to have, well, let's say this. Whoops. they're going to come together, and we're going to be left over with essentially it's just going to make a CH3Cl, right? So I'm just going to draw this out so we can actually see what's actually happened. I'm going to choose a different color for the C. Let's choose purple. Sorry, for a chlorine. Plus, we have got so we've got this chlorine reacting with the CH3 radical, and of course we've got this chlorine radical left over. So plus Cl dot. That is all there is to it. This is the first step. This is the second step. Now you'll notice in both of the propagation steps we have got a radical on either side of the arrow. We've got one on the left, we've got a chlorine radical on the left here, we've got a CH3 radical on the right here. On reaction 2 we've got a CH3 radical on the left, and we've got a Cl radical on the right. So propagation steps, right, we will always have a radical on the left and a radical on the right. And you'll also notice that, you know what, we started off with this Cl radical, and you know what, we've also finished off with a Cl radical, right? What we've done is we've regenerated the chlorine radical. We've regenerated the chlorine radical. Essentially, this is the substitution of the haloalkane. We started off with CH4, and we've now got our end product of this. We started off with CH4, we've now got CH3Cl, which obviously one of the hydrogens have been substituted for chlorine. So essentially it should really be done, right? Well, not quite, because we've still got this radical left over. So what happens to these radicals? Well, this is where the final stage, or the final step, comes into play, and this step is known as termination. And as the name suggests, this is when two radicals combine to form a molecule. And it matters not which two radicals come together, right? What can happen is, essentially, a chlorine radical, because that's what we ended up with last, can react with another chlorine radical. Yep, you guessed it, it's going to make a Cl2. Or we could have, if I was to show the arrows, something like this, something like that, just coming together. Or we could have, well, let's have a look, the second, another radical that we've made in this reaction so far is the CH3 radical, right? So we could have CH3, right? And we could react it with a CH3. So again, same thing. It doesn't matter whether the arrows go up or down, it just makes it a little easier to see sometimes, right? So again, two CH3s coming together will simply make C2H6, right? Ethane. And the last possibility we can have is, of course, a methyl radical reacting with a chlorine radical. And a chlorine radical. And again, whoops, that's a little... to make CH3Cl, which is what the product was in the last step there. That is all there is to it. So you might wonder, what is the point of the termination reaction? Well, essentially, termination just removes the radicals, which stops the reaction. If there's no radicals, we can't have a propagation reaction going on. So it stops the reaction, right? It stops the reaction. The propagation step is essentially a chain reaction, you see. So it stops the reaction. That's all there is to the radical substitution of alkanes. In this example, in this clip, we've used chlorine. You could of course have bromine. It doesn't matter because it's just another halogen. You could have iodine. It matters not. the steps would be the same in each case, as would the conditions. There's one thing I'd just like you to be aware of though, and it's coming back to the propagation step. Essentially, I've stopped this propagation step after 2 reactions, right, until we've got this CH3Cl. But what can happen is this CH3Cl can now take part in reaction 1 of the propagation step, and it takes the place of this methane here. It can take the place of this methane. So essentially what's going to happen again after a repeated propagation reaction, we're going to form CH2Cl2. Again, this can also take the place again of the methane, and if it was to go through the repeated 2-step process of propagation, you would get CHCl3. As you can see, each time we're just substituting a hydrogen for a chlorine, and of course you can go through it once more to make CCl4. So the 4 products that we can make from the radical substitution of chlorine with methane are these 4. That's 1, 2, 3, and 4. You should be able to name those. I'll leave those to you to try and practice the IUPAC rules that we've done in class. Now this was a little long, but I hope that it's helped. Yeah, thanks for listening.